Hello, everyone. Good afternoon. I'm going to talk about the uniform thermal scheduler for deep neural network in 3D stacked systems. 3D stacked system, as the name suggests, involving stack dies together, including the cores and the memory. This architecture enables heterogeneous integration, improving the space efficiency. Different components in the die are interconnected through silicon vias, which are compact material and offering the higher bandwidth and lower latency. As a result, 3D stacked system chip alleviate the memory war and provide the next generation computing power. However, while 3D stacked system bring significant advantages, they also introduce several challenges. For example, the manufacturing cost is high, and which make research and accelerating scientific discovery depend on the simulations. We use the state-of-art simulator called COIN for our research. Additionally, the integration of the cores and the memory in a 3D architecture increased the power density compared with the 2D counterpart. Without effective heat dissipation techniques, the heat not only transform horizontally, but also vertically, accelerating the thermal conditions. Currently, there are a lot of 3D stacked chip available in the market. Leading manufacturers like Samsung, Intel, AMD, and also Apple have developed their own 3D stacked products, showcase the growing adoption of this technology. In 2D architecture, the DVFS, the dynamic voltage frequency scaling, is typically used to regulate the frequency and voltage of cores. However, this approach is insufficient for 3D stacked architecture. For example, when we run the benchmark called a string cluster at different constraint frequency, even at the 1 gigahertz, the peak temperature will exceed the thermal threshold at 75 degrees Celsius. Furthermore, running tasks at such low frequency will significantly reduce the system's performance, highlight the limitation of the DVFS alone for the core in managing the thermal challenges. So thermal management in 3D system generally involves controlling the behavior not only for the cores. We also need to take actions in the memory banks. For process, DVFS is dynamically coordinate the frequency voltage, but we also need to reduce the active behavior of the memory bank. So I will give you a motivational example. We have two scenarios, and in scenario 1, we just let the core run at 4.7 gigahertz without placing any memory bank to the low power model. In the scenario 2, we put the first 14 memory bank into the low power model, and we control the core frequency set to 4 gigahertz, and then we show we can clearly see the first scenario. They can hard to meet the thermal management, the thermal constraint, and with sacrifice not of performance. The second scenario, we combine the memory. The low power model for the memory bank and also the DVFS for the core. Then we coordinate it together, and we can achieve the good system performance. This is the implementation of the low power model, I will not go into too much details about the low power model implementation. And the key points is when the power bank is switched to the low power model, then the data is keep it in situ without any migration. And but this constraint, when the memory bank is switched to the low power model, this data is inaccessible, and we only need to consume a tiny part of power to keep this data. And if we want to reaccess the data, then we need to reactivate this memory bank and fetch the data, which increase the latency. So this low power model design is also not free. Then how to propose a unified scheduler? On the one hand, we should do the DBFS for the cores, and on the other hand, we applying the low power model for the memory bank. Then we devise a deep learning method to do that. Because of the design space is huge and is exponentially large, then we use the embedding space to compress this design space. Like the large language models token, they use the embedding space in the hidden space to compress the language token. We borrow this idea and into this design space, and we also design a very tiny neural network for predicted Q value, and the result shows the compaction of the embedding space is effective. We also verify our approach not only for the classical, PASIC, and the SPLASH2, that kind of for classical benchmark. We also verify it in the deep neural network like AlexNet, ResNet, and it works very fine, not only for the performance, also for the energy consumption. So let's draw the conclusion, and we propose a unified scheduler not only for the core but also for the memory bank to do the thermal management for 3D stacked architecture, and we achieved a good performance while keep the system security safe, thermal safe.